Okay, what we're going to be looking at here is a projectile launched at an angle. Now, there are two types of problems you're going to see in this kind of category. One is when the initial height is equal to the final height. So we're launching from a certain height, and then the projectile is going to land at the same height. And the other is if the projectile lands at a different height. Now, for this problem, we have a projectile launched from the ground, and then we're interested in when it hits the ground again. So this is going to be a problem where our initial height is equal to our final height. Okay, so let's take a look at this. So we have a projectile launched from the ground, and it has a velocity of 100 meters per second, and it's at an angle of 15 degrees relative to the horizontal. So what that's going to look like is we have a projectile on the ground, and it's going to have this parabolic path, and it's going to go up and down, and it's eventually going to land at the same height that it started at. Okay? Now for all of these problems, you're given the initial velocity. But that velocity is at an angle. So what you need to calculate is the initial x velocity and the initial y velocity. And you do this by resolving the vector components. So for this problem, we have a projectile launched with an initial velocity of 100 meters per second. So it's launched at an angle, and we know that the angle, according to the problem, is 15 degrees relative to the horizontal. So what we can do is we can draw in the horizontal and vertical components of our initial velocity. So what we do is we put our two vectors head to tail so that they go from the origin to the tip of this resultant vector. Now, in order to figure out the values or the magnitudes of the x and y velocity, we just have to do some simple trigonometry. So I know the hypotenuse of this right triangle, and I know this angle here is 15 degrees. And so I can do sine of 15 is equal to the initial y velocity over 100. Now, how did I know to use sine of 15 is equal to this ratio? Well, sine is opposite over hypotenuse. So I have two of the three components, and so I can algebraically solve for the third. So for this, all I have to do is multiply by 100 on both sides, and I get the initial velocity in the y direction is 100 times the sine of 15. And if we just punch that into our calculator, 100 sine 15, I end up getting 25.9 meters per second. But we can generalize this formula. And if we call the angle theta, we can say that the initial y velocity is equal to the initial velocity, in this case 100, times the sine of theta. We can use a similar strategy to find the initial x velocity. So instead of sine, I'm going to use cosine 15 is equal to initial x over 100. How did I get that? This is my angle, and cosine of that angle is adjacent over hypotenuse. So cosine of 15 is equal to adjacent initial x velocity over 100. I can rearrange this by multiplying by 100 on both sides, and I can say my initial x velocity is equal to 100 times the cosine of 15. And so I put that into my calculator, and I get 96.6 meters per second. We can write a general formula up here, same as for our initial y velocity, is equal to our initial velocity that's given times the cosine of theta. Okay, any angled projectile problem, you're going to have to do something like this. Okay, and you can draw out your picture, but these are the formulas that you're going to be using to figure out these components, and this is how they're generated. Okay, so the first part of the question is asking, for how much time is the projectile going to be airborne? So for any problem where the initial height is equal to the final height, you can use the following strategy. So I'm going to go down here. What we need to do is we need to figure out the time to the peak. So I need to find out how long does it take for this projectile to reach its peak. We know some information about the motion of this projectile. So in order to reach the peak, the x component of velocity does not matter. Only the y component matters. Okay, and you've done problems like this. So I know that my acceleration in the y direction is negative 9.81 meters per second squared. I know that my initial velocity in the y direction is 25.9 meters per second, right? We calculated that up here. You also know that at the peak of flight, my velocity of interest is 0 meters per second. So at the peak, my velocity is 0. So if we use what I call my second favorite equation, which looks like this, but we write it in terms of y, so I'm going to change it now and write it in terms of y. What you'll notice is that we have 3 out of these 4 terms. And so we can algebraically solve for time to figure out how long it takes to get to the peak by plugging these 3 values into this equation. So I know that my velocity of interest, my velocity at the peak, is 0. I know that my acceleration is negative 9.81 meters per second squared. I don't know time. And I know that my initial velocity in the y direction is 25.9 meters per second. So if I subtract 25.9 on both sides, and then I divide 25.9 divided by 9.81, I end up getting that it takes 2.64 seconds to reach the peak. Now, for a problem where the initial height is equal to the final height, that accounts for half the time. So if the initial height is equal to the final height, if I want to know how much time the projectile will be airborne, the time to peak accounts for half of the time. So the time airborne is equal to 2 times the time to peak. So the time in the air is equal to 2.64 times 2, which is 5.28 seconds. Again, this only works if your initial height is equal to your final height. Okay, so that's the answer to the first bullet point. How much time is the projectile airborne? 5.28 seconds. How far from the origin will the projectile land on the ground? So what this is asking for is a horizontal distance. What is the horizontal distance that the projectile will go? So if I'm looking at the horizontal distance, I know a few things about the horizontal trajectory. I know that the acceleration in the x direction for all of these problems is 0 meters per second. Once it's launched, its velocity in the x direction is constant. I know that my initial velocity in the x direction, because my velocity is constant, is equal to any velocity in the x direction during flight, which is 96.6 meters per second. We calculated that up here. And I know that the time of flight we're going to call that t, is 5.28 seconds. So I can use one of my favorite formulas, x equals 1/2 at squared I know that my acceleration in the x direction is 0, so this term is going to be ignored. And I know that we're just going to call my initial position 0. So x is equal to the position at which the projectile lands, our position of interest, is equal to our initial velocity in the x direction times time. So all you have to do is multiply 96.6 times the 5.28 seconds of flight. So where it lands is 510 meters from the origin. So how far from the origin will the projectile land on the ground? 510 meters. So that's it. So if the initial height is equal to the final height, you can, well, what you'll have to do is you're going to have to calculate the x and y components of your initial velocity. You're going to have to find the time to the peak using this equation. And then you're going to have to calculate the time in the air. The time to the peak is half of the time of flight, only when the initial height is equal to the final height. So you'll just multiply that by 2. So the time in the air is going to be 5.28 seconds. You're then going to use your initial x velocity and the time you calculated, the time to peak, in order to find how far the projectile flies in the x or the horizontal direction. So that's it.